Okay, so we continue from where we stopped last time. So remember, we said that basically once you fix an ordered basis, then of a finite dimensional vector space, this gives us a unique. This gives us basically a one-to-one correspondence between vectors in the vector space, which are linear combinations of the basis vectors. And since we have fixed this basis in this order, we get the coefficients in the same order. And we write them as a column vector, transpose of a row vector. And so we define this map to be the square bracket B map. This is the coefficient map, which takes a vector to the tuple of coefficients with respect to the given basis, okay, in F to the n. And with this map as the definition, we have this theorem, so we will start today by proving this theorem. Suppose V and W are finite dimensional vector spaces, and these are the ordered bases that we also fix, okay, of V and of W. So V has basis size n, W has basis size m. Given a map from V to W, a linear map, there exists a unique matrix AT such that the equation that you satisfy is the function. Right? So I said this last time. Let me remove these distractions. And such that for all vectors V, if you look at the matrix with respect to B prime of T of V, of the image of V, then that equals the same. That is the same as just looking at the vectors here and acting by the matrix. So basically, this is by the matrix that exists. So this is basically saying that I can reduce linear transformations to matrices acting on vectors. Okay, and this is of course once you have fixed these two ordered bases. Okay, so before I prove this theorem, then yeah, so maybe some notation and then the proof, right? So notation, example, and proof. So definition. We will also write AT as AT by, I'll write down in the same exact way, just like we write down V with respect to the coordinates and T, I will write this down in the very same way like matrix multiplication. First V prime and then V, so that the equation here, this equation, so that the theorem says now says that if you look at TV V prime, and this is equal to T times V. And then you know what to do. This was B, so this must be B prime and V. Just like matrix multiplication, the B and the B are together, they cancel for all V in F to the n, for all V in V. Sorry, even this was actually, I think, wrong. This was wrong. This should be V in V. The point is, V is a vector space with n dimensions, but once you bring this operation in, then you reduce to F to the n. Before that, you are still in V. Okay, so that's what the theorem says. Examples. Example. Let's say. Okay, yeah. So let's look at an example. So what I say, let's look at the transformation. So V equals, so the field is a real line, the real numbers. Okay, the vector space V and W are both the same vector space, which is the plane. And T is the operation of rotating counterclockwise by 90 degrees, let's say. And I will even, so I have the same vector space and I have the same basis also. Let's say I'll just keep the same. Right? Okay, so first of all, before I write down the basis, notice that this operation does not need any basis, right? I can tell you what this operation is without writing down the basis. It did not need a basis to be stated. Did not need a basis for its definition, for defining it. Right? So, I mean, I have a vector in the plane. All I do is rotate it by 90 degrees. Assuming I can draw 90-degree maps correctly. So, this is V, this is T. I don't need to define any like X and Y axes. I just need the origin. I have a vector, I rotate it by 90 degrees. It's very, very simple. Okay? But now let us actually choose ordered bases and write down the linear transformation of this, the matrix of this linear transformation. Now choose set, let's say, B and B prime to both be the same bases. E1, sorry, it's an ordered pair, so it's an ordered pair. E1, comma E2. Then what is the basis, right? So now, well, E1, now you see E1 goes to what? E1 goes to E2, and E2 goes to minus E1. So you can check that AT, I think this should be 0, 1 and minus 1, 0 if I'm not wrong. Apparently the other way around. 0, minus 1, 1, 0. How do you check whether, how do you check whether it was the previous matrix or this one? Well, let's multiply it out. So, right, so let's check. We are claiming that this is true. So let us check that it is. Indeed. Why? So let's look at AT acting on 1, 0. Well, 1, 0. So AT is supposed to be the matrix P with respect to B and B. 1, 0 is supposed to be the coordinates of some vector in the plane with respect to 1 and 0, this basis. So 1 times E1 plus 0 times E2. So that means it is the coordinates of E1, 1 times E1 plus 0 times E2 with respect to B. Okay, and how much do we get? This times E1 is this times 0 and then 1. So you get, indeed you get 0 and 1. So check, if you multiply this matrix by that vector, you get 0, 1. And this is exactly, what is this? This is exactly E2. But E2 is indeed the rotation of E1. So this is correct. And similarly, if you look at AT times 0, 1, you get minus 1, 0. And this is indeed minus E1 B. This is E2B. And this is exactly T, E2. Okay, so that's why this is true. Okay, so that's the, this is one example, that's the definition that we're writing down. Okay, so now let's prove the theorem. There is a unique matrix. I think that is, the theorem proof is not very hard. So let's write down what it means. So we have ordered bases, right? So let us write this down. Let's write down T, V, I or Vj. I need to look at my notations. Do I say Vj? I say Vj. So proof of theorem now. Now we will prove it. Okay, so proof. Let's see. So write down. So write T of Vj. Remember, Vj is some vector. It's a basis vector, but it is some vector. Now this is a vector in W. That means it can be written as a linear combination of vectors in W. So I goes from 1 to m. Let's call it Aij, Cij, Aij, I guess, because the matrix is going to be Aij, Wi. Okay. So now the point is these guys are of course unique because W's form a basis as the Wi form a basis. Okay. Okay, once you have these things are unique, then I have my matrix A. So what is the dimension? When the i's go from 1 to m, the j's go from 1 to n. And so this is indeed M cross N is uniquely defined. Is uniquely specified. And it satisfies what? Let us say. And let's say, okay. And if V equals summation Cj Vj, so j goes from 1 to n, then let's calculate what we get. Then first of all, we have V B is just C1, C2, Cn. Okay? We have A is this thing, fine. And now what is T? TV is T applied to this linear combination. So first of all, it is summation Cj, T of Vj, that's by linearity. But now each T of Vj is written in this way. So I write this down, I equals 1 to M Cj Aij. Okay? And then times Wi. But now all I do is I interchange the two summations. These are finite sums, so you can interchange without any fear. So I goes from 1 to M, J goes from 1 to N, and I will write down Aij Cj Wi. So what are the coordinates of TV? This is what TV is as a vector. So when I just write down the coordinates of each Wi together, what do I get? Let's see. Implies that the coordinates of TV with respect to the basis B prime are what? It is literally, I'll write this down as a vector and then transpose it. So it's summation A1j, the coefficient of W1, Cj, A2j, Cj, and so on, Amj, Cj. Every sum is from j goes from 1 to n. But you see, what is this? These are precisely the entries of A times C, the first coordinate, A times C, the second coordinate. And A times C, the nth coordinate. Nth coordinate, the whole thing transposed. And that is exactly the vector A times C. Because it's the first coordinate, second coordinate, third coordinate. Any vector is equal to its first coordinate, its second coordinate, and so on. But A times C is equal to its first coordinate, its second coordinate, all the way transposed. But what is this? This is precisely, so this is called AT. AT, and what was C? C itself was this vector B. And that's what we wanted to prove. There is a unique matrix such that this happens. Well, so first of all, we have seen that this matrix satisfies this problem. Okay? And as far as the uniqueness goes, I'll probably leave it to you guys. But basically, the idea is take any matrix that satisfies this equation, that TVB prime is AT times BB, and then just check it entry by entry. How do you check it entry by entry? Put each V to be the V1, V2, Vn. You get all the columns correctly. And what you get is exactly these edges. Just maybe I'll say that. Let me say that. For uniqueness, to see why the A is unique, to show this AT is unique. Unique among what? Unique among the matrices satisfying this equality, that this equals this. Let A be any other matrix, any matrix, such that this happens. TV B prime equals A times BB for all B, for all B in B. Now what do you do? Well, now what you do is the following. 1 second, let me write this down. Okay, so what do you do then? Well, it's very simple. So as I said, set B equals Vi, set B equals Vj from above. Then what we get is, then that means that what is this Vb? It is exactly Ej. Sorry, so Vb equals Ej, not Ej equals Vb. The coordinate vector of Vj is literally 0 times E1 plus 0 times E2 dot dot plus 1 times E Vj. So that means it has 1 in the jth coordinate and 0 elsewhere. Okay. Now, let's write now let's calculate. This much should be enough to prove it. It's good because I want to use this AIJs. Now, let's write down A times BB. So on the one hand, okay, I will do it this following way. A times VB. This is A times EJ. Okay. Let's call this A prime. Sorry. So because I've already used AIJ, so let's use A primes. Okay. So A prime is any other matrix. What is any matrix times EJ? Remember, it is the first column times the first entry, second column times second entry, and so on. So this is literally the jth column. A prime 1j dot dot A prime mj. So on the one hand, this is literally a matrix times the EJ vector, so you get the jth column of this matrix. Of A prime. Okay? This is what this vector is, because that's this. On the other hand, A prime times VB by assumption is PV. Sorry, this is not VB, this is VJ. I should just write VJ. TVJ, and now it's in V prime. Well, but what is TVJ V prime? TVJ V prime we wrote down was exactly this. It is the coordinate of B prime of summation Aij Wj. Wi. The J is fixed, but the I runs over 1 through M. So what is the coordinates of these? Well, in this basis, and you're writing in this way, you get A1j, A and J. And so what we showed was that if you start with any matrix satisfying this property, then on the one hand, A prime Vj is just the column of A, which is the jth column of A. On the other hand, this guy is precisely the jth column of A. This is the jth column of A prime. This is the jth column of A. And we are getting that these are equal. So and this is equal for all j. So every column of A prime and the same corresponding column of A agree, therefore A prime equals A. And so there indeed exists a unique matrix. So it's not too much more, but you have to write down this calculation and check. And that's indeed the case. Okay, so basically this means that given any linear transformation and fixing the order bases of the domain and codomain, you get a unique matrix. Okay, great. Beyond that, now let's continue. Okay, what next? That was that. Okay, now corollary. The fact is that, so that means we get a matrix, so we have a map from lin VW to f to the m times n, sending t to at. Right? We just have a map of, it's a set theoretic map. There's a unique such matrix, so it's a well-defined map. And now the claim is that this map is isomorphism. Fix V and W over F and order bases. B, whatever is B1, B2, Bn, and B prime is W1, W2, Wn of v comma w respectively. Oops. The map T goes to AT, which is just T in those bases, B prime comma B, is a linear isomorphism. From then that means. Okay, am I going to prove this? Well, sure. I don't think this is a homework, so I should prove it. Maybe I should change pens first. Use this one for enough. Okay, so how do you prove this? Let's see. Okay, so the map is clear. Now we have to just look at the fact that first of all that the map is linear, then it's 1 to 1, then it's on to it. So proof. Let's give this map a name. Let's call this map. I'll give it a name, a nice name. It's a Greek letter maybe. Eta. Okay, so eta is linear. So we have to prove three things. Eta is linear, eta is 1 to 1, eta is onto. Okay, so now why is eta linear? Well, so let's look at this. So I think again to prove that a map is linear, it's enough to check that suppose you have given T and T prime in lin VW and the scalar. I want to show that eta of, we want to show what we want to show? We want to show eta of T, Ct plus T prime. So we want to show the usual condition, C times T plus T prime. Remember, you know how to rescale and add. You know that this is a vector space. So C times T plus T prime makes sense as a linear transformation, right? Evaluated at any vector V, it is C times T of V plus T prime of V. Okay, so that we already defined last time. We want to show this is equal to C times eta of T plus T prime. Sorry, eta of T prime. Okay, now why is this true? So you can check, so the way that you show that two linear transformations are the same is by evaluating at every vector, right? So eta, of course, these are matrices. Fine. So did I say this last time? I hope I did, right? That two matrices are the same if and only if they are the same, then you act on every vector. Am I going to say it next? This is where I'm going to say it next. Fine. So, okay, I'll first remind you of a homework problem, which will give you. So, two matrices A and B, or A and A prime. Yeah, let's call it A and A prime. So you see the connection to. Well, let's say A and B. So this is like my matrix A. This whole thing is A. Eta gives you a matrix, and the whole thing here is B. It belongs to F to the M cross N. So the matrices are over the same field of the same sizes are equal if and only if. Basically something like this. Two matrices are equal if and only if their JX columns are equal. Right? So if and only if AV equals BV for all V in F to the N. Or if and only if like this, if you put A times EJ and B times EJ, then those are equal for all j. Because these are just the jth columns. If and only all the columns are equal, then of course. Okay, so that's great. That's basically I told you the solution, I think. If they are equal, then this happens. If this happens, then this happens. And if this happens, the columns are equal, so that happens. So that's just obvious, but fine. Now, given this homework problem or given this question, I want to show these two matrices are equal, so I can just multiply by ej and check that they are both equal, right? So applying this here. So we want to show this, right? So let's just fix. So let 1 less equals j less equals n. N is the dimension of v, and compute or evaluate a compute. Let's compute. So this times ej, a times ej, is eta of Cp plus T prime. Okay. Applied to ej. But what is ej? Ej is precisely Vj in this basis. And this guy is just, I can replace this by b prime b, because that's exactly what eta does. But now by the previous theorem or whatever, we have this theorem. I write THM for theorem. This is exactly Cp plus T prime applied to Vj in the new basis b prime. And for vectors, we know that certainly addition and so on is fine. So let's see. So first of all, I write this as C times T of Vj plus T prime of Vj b prime. And I think I said last time that the map sending a vector v to the tuple v prime to vb is a vector space isomorphism from f to the n. That was the homework problem I gave you last time, right? So therefore, this thing, because it's a vector space problem, this is over vector spaces from the previous homework. This is equal to its linear map. Therefore, I can write down everything. C times T Vj plus T prime Vj. That's from now. But now I can write this down. This is exactly what is T Vj. It is, let's convert it back now to the, again use the theorem to convert it back. And so what we get is equals C times T b prime b Vj b. Frankly, I did not need to say Vj. I could have said V for any V. It doesn't matter, but fine. Let's just do Vj. So Vj b plus T prime b prime b Vj b. Right? That is again by the theorem, but going in the reverse direction. But now, what is this b prime b map? This is exactly eta. So this is C times eta of T. This is the matrix applied. This is the matrix multiplied by the vector Ej, because Vj was Ej here, plus eta of T prime times Vj. Okay, and now I regroup this to say that this is equal to C eta of T plus eta of T prime Ej. So I started with A times Ej, where A was this matrix, and I ended up with B times Ej, where B was this matrix. And now you see the two matrices are equal if and only Aej equals Bj for all j. Well, this is what I just got. I started from Aej and got to Bj. And this is true for all j. So by this homework problem, A equals B. Meaning that these two matrices are equal. So this is just the proof that beta is linear, i.e. eta is linear. Okay, so this is how you spell things out in full detail. But you can. The point is we have defined everything consistently. And so you can spell things out in full detail. And that's the point of this course. This is a rigorous course with proofs. So we're supposed to prove things, right? So you can't jump over steps. Okay, the second thing now is that this is 1 to 1 and 1 to 2. So let's check 1 to 1. Because this is a linear map, to check 1 to 1, it's enough to check that the kernel is 0. So suppose eta of t is 0. This was A, B, I haven't shown you rank nullity, and therefore I can't use something else. That's the point. We are getting towards rank nullity. Fine. So let's do 1 to 1. So eta is 1 to 1 because let's see. So it's enough to, so since eta is linear by A, enough to show eta, the kernel of eta is 0, to check that the kernel is precisely the maps taking eta, the linear maps that are sent by eta to 0. And this is the 0 meaning the 0 linear map. Okay. So now say eta of t is 0. Right? This is the 0 matrix M cross N. Because eta, the image of eta are matrices. So the claim is only the 0 matrix can work. Okay. So again, let's multiply that by ej. So 0, the 0 vector is 0 times ej, 0 matrix times ej. But that is the same as saying, well, this is eta of t times vj b. But what is eta of t? Again, this is equal to, again, as you know, as t b prime b vj b. But then by the theorem, this is equal to t vj b prime. Right? So the coordinates of this vector with respect to the basis are 0. The only thing that means is implies this vector is 0 in the W vector space for all 0. Well, this linear transformation takes an entire basis to 0. If it takes a basis to 0, then by linearity it takes every vector to 0. And there is only one linear transformation that takes every vector to 0. That is the 0 transformation. 0. So that is exactly 1 to 1. And then finally, eta is on 2. That is where I'm going to wonder what to do, because I want to tell you about the basis as well. So should I just do it and then tell them about the basis? Maybe I should. Eta is on 2. One second. What am I doing after this? Composition. I don't need composition right now. Tell me basis of the vector. I can tell you basis and rank nullity right away. So let's skip this. One second, please hold on. Okay. So why is eta on 2? I want to show that you get to every matrix, right? Okay, let's do this once and then we will directly go to the general version. Eta is onto for the following reason. How do you show that a linear map is onto, right? To show that a linear map, let's say T from V to W is onto, it suffices to show that every basis of W is in the image of the map. Because if every basis of W is in the image, then the span of that basis is in the image, right? You can take linear combinations of whatever you got to the basis and get to that linear combination. And if it's a basis or a spanning set, then of course you're done, right? Because then the entire vector space is in the image. It's enough to show that some basis of W is in the image of T. Okay? And that's what, this is the principle we are going to apply here. Apply here to, what is W now? It's not the W and V from the theorem, it's the, let's call it V prime and W prime. That makes it easier. And I'll apply this to W prime equals the set of matrices, the vector space of matrices. V prime is lin VW, W prime is F to the n cross n, which has a basis of the elementary matrices, right? EIJs. A standard basis. I'll put it in quotes because we are used to seeing the standard basis only for the F to the n, but yeah. A set of all EIJ, right? Elementary matrices where EIJ has 1 in the ijth position and 0 everywhere else. And clearly every matrix is a unique linear combination of these EIJ. So it's enough to show that there is one linear transformation which goes to EIJ. And let me tell you that linear transformation. So define Tij from V to W, which sends by sending summation Cj Vj, j equals 1 to n, to what? Oops. Let's not call this I. Let's call this as j prime. So Cj prime Vj prime to Cj Wi. Okay, the claim is this is linear. I will ask you guys to check that this is linear. It's very trivial. It's take c times this plus some other expression like this, and check that it maps correctly. Check that Tij. Oh, so I should mention here that here I goes from 1 to n and m. For 1 less equals I less equals m, and 1 less equals j less equals n by sending this thing. So claim is check that Tij is linear. Okay, I'm just checking onto. So I'm not saying that these are linearly independent, but in fact they are actually a basis. But we will get to that in the very next board. But it's okay. Check Tij is linear, and moreover, so check Tij is linear. Full stop. Now, what is the basis? What is the matrix of Tij? By the previous theorem, it's a unique matrix, right? If I can produce some matrix that acts the same way that Tij does, then I'm done. Well, let's look at what it does to the CJVJ, right? So clearly, let's look at what this does, right? So if you look at this matrix and you act on the vectors C1, C2, Cn, what are you getting? You are getting Cj in the ith position. So when you take this is let's call this as the vector V. Let's call this as T of V. Okay, so Then let me write this on the next board. So clearly, if you look at this is V, right? So eta of Tij acting on VB. So on the one hand, this is equal to what? It is eta of Tij, whatever this matrix is, acting on the vector C1, C2, Cn. Because VB is C1, C2, Cn. V is just Cj. On the other hand, by the theorem, this is equal to the Tij acting on V with respect to the new coordinates, the new basis W, W1, W2, W. And what is this? Well, this is Cj Wi. So this is literally Cj times the ith vector Ei. Because the Wi is the vector with just 1 in the ith position times Cj. So Cj in the ith position and zeros everywhere else. So this thing times C is this thing. But on the other hand, you see that this is exactly equal. If you compute the Eij matrix times this vector, then you can check that what you get is Cj times Ei. So on the one hand, you have this times the C vector equals this. On the other hand, Eij times the C vector equals this. So eta of Tij times the C vector equals Eij times the C vector for all C vectors belong to F to the N. But then this is exactly one of the homeworks I just told you. This happens for all vectors if and only the matrices are equal. And in many cases, this matrix was supposed to be unique. So indeed this is equal. Therefore, the Eij's belong to the image of this thing. Therefore, their span, which is the entire space, belongs to the image of eta, and therefore eta is constant. So the idea is very simple. To prove that a map is onto, a linear map is onto, prove that the vector space, which is the codomain, whether the basis of that vector space belongs to the image of this map. And that's what we did. And so now let me tell you slightly more generally about a basis of any space of linear transformations. So I'm going to skip 2 pages in my notes. We will do those later, probably next week. If we don't find time today, and I doubt we will find time today. But this is a very natural thing. I just told you I just told you that these are sort of nice elements. Actually, as I said, they turn out to be basis vectors. Let me tell you this. So more generally now, we are going to talk about a basis of the linear space of maps V, W. And I don't care what W is. W can be infinite dimensional. I just care that V is finite dimensional. For V, finite dimensional. Okay, so say, maybe I'll just write these down. So I'll write down I'll just call it a theorem and write down all the notation inside it. Theorem. Say V and W are vector spaces over F. Okay, I'm writing down the basis of linear transformations, so I'm not writing down matrices. So I will not write down ordered bases, okay, in this case. With V has a basis. Oh, sorry, let's say with bases. V1, Vn, and as I said, every vector space has a basis if you believe in the axiom of choice. So I don't care if I have a basis that's indexed by an arbitrary set I. If my arbitrary set I is finite, then this vector space is finite dimensional. If not, then it is infinite dimensional. Okay? And now I'm assuming that these are non-empty. So let's call them 0 not equals. Okay? So neither vector space is 0. So that both of these sets are non-zero, non-empty. Okay. Now, so now let me define these Tijs again. So for all, oh, I'm so sorry. Uh, 1 second. Maybe I should do this slightly better. So, 1 second. Okay. I just need to make a couple of small changes. The mistake I made wasn't using I. I should be using J, right? Because we just said WJ. Fine, we'll do that. Okay, fine. So let's first of all change this. WJ. Okay, now define for let's say 1 less equals L less equals N and J in J. Define T. Yeah, I don't want to keep I and J on the same footing. So because you might think they're both finite or they're both infinite. Here J can be infinite, so I'm just going to use L instead of I. It looks like I, but it's not. Define TLJ from V to W. Via the map. So TLJ of summation CJ C. Oh good God. So summation CJ prime, VJ prime. J prime goes from 1 to L. Exactly the same way, right? Except instead of I, I'm going to use L. So it is CJ W I. No, something is very wrong here. WL. That's correct. That's correct. Okay. So this is the definition. And then the theorem. So once you define this, the theorem says, I mean, this is all not a theorem. This is definitions, right? With this notation, with these definitions. So what we have done is exactly the same thing here. Okay? We have done nothing different. We have defined Tij here, we have defined TLJ here. And the only reason is because I'm using L to denote the V1, V2, Vn rather than I to denote something is very. Oh God, I made it worse, didn't I? Those were supposed to be L's. So what did I do here? No, okay, this is going to be a mess. So, but I'll do it correctly. Let's write this one correctly. These should all be I's. This was all correct. Fine. Let's just do 1 less than J less than N. Let's just do Tij. We will just do it using the previous notation. My apologies for this notational business. Okay. Okay, so just the same thing, exactly the same thing as we did, except I don't say I less equals M here. I say I belongs to I. That's so define Tij in this way. Then the theorem says, then Tij, oops, I can't repeat the same spelling, there are subscripts. Tij is linear. Or maybe I should say R linear, then the Tij's. Then the maps Tij are linear and form a basis. Lin-Vila. That is the theorem. Okay, so let us prove this. I'm going to check. Well, maybe I won't check that Tij is linear, because otherwise, what was the point of telling you to check this? It would be the same thing. So I'll leave it to you to check that it's linear. But let me check that it's 1-to-1 and 1-to once again. And the claim is that the proof is exactly the same as there. Yeah, so proof. Check linearity yourselves. Okay, this is part A. Part B, Tij is 1-to-1. Again, the same thing. We've seen this, like, I think twice today itself. You have to check that the kernel is 0. So say Tij of some vector is 0. Well, some vector is summation v, let's call it Cj prime, Vj prime. Equals 0 in W. J prime goes from 1 to n. Well, what is Tij of Vj prime or this thing? This means Cj times Wi is 0. Oh God, this is very silly, right? Of course, I want to say this is not a linear. Oh, sorry, this is fine. Linear is fine, but this is not 1-to-1. We want to check if linearly independent, and we want to check the spanning set. Are linearly independent. I'm not even thinking straight at this point. Yeah. So suppose, okay. Say, let's give this some coefficient. Cij, Tij is 0. And what do I mean by 0? I mean it is the linear transformation 0. I in I and j less equals n. This is a 0 transformation. Well, if it's a 0 transformation on the vector space, then it is equal to 0 when evaluated at every vector, in particular at every basis vector, Vj prime. So, equals 0 W when evaluated, or not, I don't need to say when evaluated, at every Vj, okay. Vj prime. So let's compute this evaluated at Vj prime. Sorry, sorry. So what we said was 0W equals this summation evaluated at Vj prime. But what is Vj prime? What is this vector at Vj prime? It is summation Cij times Tij evaluated at Vj prime. By the way, I should mention that when you do linear independence, you only look at a finite sum. So we are only looking at a finite sum of things here. Okay? The remaining Cij's have to be 0. Okay, so therefore I get the finite sum, but what do I get? I get Cij times Tij of Vj prime. And Tij of Vj prime is very simply Cj Wi. So you get summation Cij or Vj prime, right? Let's do this quickly. What do I get when I evaluate this? So let's write this down carefully. Cij Tij of Vj prime. Let's look at Tij of Vj prime, right? Suppose Vj prime has a coefficient of 1 and the other others have coefficient of 0. So if this j, look, from this j I would get the same j. Okay? Now if instead of this I had only one Vj prime and the j prime was not equal to j, I would get a 0 here. Because 0 times that Vj prime plus Cj times that Vj. So I only care about the coefficient corresponding of the vector matching this one. Right? So therefore, unless these two are equal, the answer is 0. So what you get here really, this is I comma j. So what you get is, first of all, you get so you get summation with I in I, Cij prime, as I said, unless this J matches J prime, you get 0. J prime is given to us. So Cij prime Wi. Okay. And now you see that this is 0 W. So the Wi's form a basis. This is a finite sum. And you get that this finite linear combination of a basis elements equals 0. So because the Wi's are 0, all the coefficients must be 0. For all I in I. And this was true for every Vj prime. So this is true for all J prime less equals n. For all 1 less equals J prime less equals n. And so that means that every single coefficient must be 0. And that's what we wanted. If we know that these things are a linear combination is 0, of course this is a finite sum. Again, let me remind you of this. Then we prove that every Cij prime is 0 for all I, and this happens for every J prime, therefore the whole thing is 0. So indeed this is linearly independent. So Tij are linearly independent. And then finally, why are they a spanning set? Well, that is also not hard. And so the basis fit. So this proof is not too hard. I didn't check the linearity, but that is even easier. With all of this, it's the same proof as for the finite dimensional situation that we were talking about just now. Okay, which I also asked you guys to prove. So part C is Tij span. Span within VW. And this is also not hard. So suppose I'm given some linear transformation. So say T belongs to within VW. Write T of Vj to be summation Cij Wi. I goes from 1 to L. Sorry, I is an I. I mean, again, this is, I'm adding that, I'm summing it up over possibly an infinite set. The idea is that it is a linear combination and a finite linear combination. So all but finitely manyCij's must be 0, and then you have a finite combination. Then the claim is what? So because there are only finitely many I in I, so look, for V1, I get finitely many Wi for which this is non-zero. For V2, I get finitely many Wi for which this is non-zero. And I do this for every I, for every J. For every Vj, I get only finitely many Wi. Right? So therefore, when I take all of those finitely many Wi for finitely many J's, that is still a finite set. And that's all I care about. So maybe I should call this. Let's define something. Let's call I naught. Let's say define I naught. Via I naught is the set of I such that Cij is non-zero for some J. Now, because for every single J, this is a finite sum, so there are only finitely many, and I said, and as a result, I naught is finite. And now I can define my T. Now I can say that indeed this thing is in the span. T is in the span of the Tij's. Okay. T is equal to summation 1 less than, sorry, let's say J less equals, J is 1 to N, summation I in I naught. So you see, this is a finite sum of the Cij. The Cij's are these Cij's, and it's a Tij. I claim that this is exactly it. And you see, that means that T belongs to the span, it's a finite linear combination, T belongs to the span of the Cij's. This would imply that the map eta is on to order. This would imply that, this would prove the theorem. Finish it. It's linear, it's one, these are linear. The maps are linear, they form a linearly independent system. and they form a spanning set. Therefore, they are a basis. So once I prove the claim, that theorem is proved. Okay, let's keep the defining equation and just write it. So how do I check that two linear transformations are equal? Again, the same thing. As long as they agree on the basis, they agree on linear combinations of the basis. Those are stacked, but the linear combinations of the basis is the entire space. So they agree on the entire space, and that just means that. So it's enough to show that proof. Enough to show, because T and everything here is linear, enough to show both sides agree on each Vj. Each V, let's call it J prime. So let's calculate. So the left hand side, so let's start with the right hand side. So RHS of Vj prime is what? It is summation J and I, whatever. So Cij Tij at Vj prime. But now Tij at Vj prime once again. So J prime is fixed. That means it has to be Cij and then Wi. This is equal to summation. Now I can delete this. Equals summation I in I naught, but I can also make that I in I because everything else is 0. Cij Wi, and that is exactly the same as T applied to Vj prime. Cij prime, so this is J prime, that's the whole part. Just T applied to Vj prime. So that is the end of the proof of the claim because both sides agree. The right hand side, this whole expression at Vj prime, agrees with T at Vj prime. Since the Vj primes form a basis, therefore these two transformations agree on the entire span of the Vj primes, which is the whole space V. So they are actually equal. But that means that T belongs to the span of the Tij's, and that means that the Tij's span the linear space. Therefore, they are already independent, they span, and therefore they are a basis. Okay, so that's the end of that proof. Okay, next, let me just take a picture here. Write this down in my notes, improve my notes. I'm recording this. I don't need to take a picture. Fine. So now that I've proved this, since we have 20 minutes, let's do the rank nullity theorem. I want to do this rank nullity theorem now. Okay. So yeah, I'll take a little bit longer maybe, but I want to finish both theorems today. One is the rank nullity theorem, and one says that the row rank equals the column rank for any matrix. Okay, so they both very naturally fit in hand. So let's just do both of them. I'll take about 5 minutes extra or something maybe, but let's see. Okay, so remember, so rank nullity theorem. So recall, let me just first remind you. So given, so I'll continue the same setting. So V and W, vector spaces over F, and V is finite dimensional. Say dimension is n. Okay. Now the rank of and of course you have a linear transformation. Okay. The first of all, the nullity of the kernel of T is, one can define it as a set of vectors which go to 0. That's the compact way of saying that is this inverse image of the 0 set, the 0 vector. The nullity of T so this is a subspace, of course, and the nullity of T is the dimension of this subspace. And similarly, the rank of T is the dimension of another subspace, which is the image of T. Remember that this was also a subspace. We mentioned that last time. Here is the theorem. Under these assumptions, the rank of T plus the nullity of T is the dimension of V, which was N. And I don't need to say N here, but I'll use N. So, okay, that's the claim. Okay, proof. The proof is not too hard actually, so that's nice. But do I want to give some examples? No, that's okay. So proof. So let's start the proof here itself. The kernel is a subspace of V, right? So the dimension of the kernel is less than the dimension of the full space because it's a subspace. You can extend the basis of the kernel to a basis of the full space, as in fact we will right now. Okay, so the dimension of the kernel. So the kernel is a subspace of V. So the dimension of the kernel, which is the nullity, is less than or equal to the dimension of V, which is N. Okay, so let us say that the nullity, of course, I am going to call the rank as R, and if R plus the nullity equals N, then I am just going to say, suppose that the nullity is N minus R. I don't know if nullity was called nullity, and that's why we write null of T, nullity, I don't know, maybe. But suppose this is N minus R. Of course, that is bigger or equal 0 because it's a dimension, or let's say it belongs to 0, comma N. Okay, it's an integer. Okay, fine. That means that there is a basis. Okay, so choose any basis. V1, Vn minus R of kernel of T and extend. So this is where we use all these things we have proved already. Extend to a basis, to a basis of V. Right? Any subspace basis can be extended to a basis using, let's give them some names, V prime 1, V prime R. Okay, I should use R here if I'm using R here. Okay. So how do I now prove that the rank nullity theorem is true? What I'm going to do is I want to find, so remember the rank is the dimension of the image of T, right? So we know that right now we know this is N minus R by name. I've called it N minus R. So it's enough to find R many vectors. It's enough to show that the rank is R, meaning it's enough to show that the dimension of the image is R, meaning it's enough to find a basis of size R of the image space. So the proof is complete. So it suffices to produce a basis of image W, image of T, of size R. So yes, I have R many vectors here, but they sit inside V. And this image of T, of course, sits inside W. So these cannot be the vectors. But they basically are, in the sense that we are going to now claim. Look at the map T acting on these vectors. The claim is that's the basis. And once we prove that, we are done. The rank nullity theorem is therefore done, right? This image is, the basis has size R. So the dimension of this rank of, the dimension of the image is R. The rank is R. The nullity by definition was N minus R. R plus N minus R equals. So that's what we need to prove. So how does one prove it's a basis? You prove it's linearly independent, and if you prove it spans, so prove. Part A, say summation ci t of v prime I equals 0. Of course, all these vectors sit inside W. Sorry, this is R, not N, that's the whole point. But well, what is ci of t of v prime I? Because t is linear, I can take, this is linear combination. So I can say it's t of summation ci v prime I. Okay? But what does that mean? It means that this vector is mapping to 0. So it means it lies in the kernel. And the kernel had a basis, this one. So let's write that down. 1 second. Yeah. So implies, let me first say it here itself, implies ci v prime I belongs to kernel of T. So which means you can find some, there exists coefficients di, dj in F such that summation ci v prime I is equal to summation dj vj. This j goes from 1 to n minus r because that's the basis of the kernel. I goes from 1 to r by choice. And now subtract. I won't write down the I goes from what to what. There is no prime here. These are primes. And now this 0 is the 0 in the vector space V. But now what do you have? You have a combination of the Vi and the Vj, V prime I and Vj. And you saw that all of these together make up a basis of V. So this is a linear combination which is 0. Therefore, all the coefficients must be 0. And so you get that the CIs are 0. But that means, well, what was it? We started with a linear combination of these vectors was 0 and end up by saying that those coefficients are 0. Which means indeed that they are linearly independent. This was part A. And similarly now part B, let us prove that it's a spanning set. Okay, why is it a spanning set? Well, this is also not that. So let me just see 1 second. This is equal to, so this is this. What was the relations? All this was this was. Okay, great. Yeah. Okay, so why is it a spanning set? That's literally 1 minute job. So take any vector in W. So this is linearly independent, and now take any vector. So let W be an image of T, right? You want to say it's a spanning set inside there, inside this subspace. Okay, implies W equals T of V for some V. For some, I'm going to write this V is summation Ci V prime I plus dj Vj. I said minus here, but that's fine. Again, I won't write down that j goes from 1 to n minus r and I goes from 1 to, I'll say I goes from 1 to r. J goes from 1 to n minus r. So W is in the image, so W is T of V for some V like this. But then what is T of V? Implies W equals V is equal to this plus this. T is additive. It's linear. It's T of summation Ci V prime I plus summation. Let's just do it everything together. It's linear, right? So because of linearity, W is summation Ci T of V prime I plus summation Vj T of Vj. But T of Vj's are in the kernel, so T of Vj is 0. So this entire sum is a linear combination of zeros. So this just vanishes. And so W is this thing. And but this vector here is obviously in the span of the T of V prime i's. So every vector in the image of T is in the span of this thing, so it's a span. So what did we see? We saw that the image of T, these guys are linearly independent subset of their image and they span the image. Therefore, indeed, they are the basis of the image. But now if they are a basis of the image and have size R, then the dimension of the image of T is R. That means the rank of T is R. The nullity is n minus R. R plus n minus R is n. And the theorem is done. Maybe I'll just say that finally. The dimension of the image is the size of the basis. Therefore, that is R, and hence rank of T plus nullity of T. The rank is R, the nullity by choice was n minus R. And that is what we wanted to prove. Okay, so that was just the rank nullity theorem. And finally, let's get to the corollary, which is the fact that the row rank of any matrix is equal to the column rank. So I can have a matrix which is like, it has 3 rows. It has 3 rows and it has 3 billion columns. You might think that the rows are independent or the columns are dependent or whatever. But regardless of how many rows and how many columns it has, look at the span of all the rows. That forms a subspace. Look at the span of all the columns. That forms a different subspace. Guess what? Those subspaces have the same dimension. That's called the row rank equals the column rank. Okay? So theorem for all application. Theorem. So maybe I should remind you, row rank equals the dimension of a row space, which is the span of all the rows of a matrix, and column rank is the dimension of the column space. I won't write that. You can figure it out. So for any matrix, for any m comma n bigger equals 1 and a matrix in F to the m cross n, the row rank of A equals the column rank of A. That is the claim. For any field, every field and this and that doesn't matter. Okay, let's prove this and then we will stop today. Okay, so how do we do this? So suppose again, so let's start. So since A is m cross n, so prove. So I'm going to use this this result, the rank nullity theorem result. So the rank nullity theorem was for linear transformations. It was not for matrices. So I'm going to first start by defining the linear transformation corresponding to this matrix. So define T, and we have seen already that it is a linear transformation. T from F to the n to F to the m. Oh yeah. T of V is just A times V. Right? So A is n cross n, this is n cross 1, and therefore you get to n cross 1. We know we have shown this is linear. We have shown T is linear. Okay. Therefore, the rank nullity theorem applies. Okay. So now, Now, okay, first of all, let's look at the rank. Then we will look at the nullity. So now T times V. So okay, let's say. So first of all, the rank. Say V equals C1, C2, Cn belongs to F to the n, and A, I write it down as U1, Un, the columns. Let's write down the matrix A as columns. I'm starting with the matrix, I write it down in the columns form. Then we know this by partition matrix kind of thing, that A times V is like taking the dot product where you take dot products with vectors. Then A times V, which is T of V, of course, is summation Ci Vi. I goes from Ci Ui, sorry. Ui. And I goes from 1 to n. Okay? That's exactly what it is. Which means it's just a linear combination of the columns. So if I run over all possible vectors V, I run over all possible linear combinations of the columns of A. Right? So what is the image? The image of T is the set of all possible outputs, which is the set of all possible linear combinations. The name for that is the span of the columns, i.e. the column space. So the image of T is the column space. Which is the column space, which means that if you take the dimension of both sides, then what is the dimension of the image? It's called the rank of T. And what is the dimension of the right hand side, the column space? It's called the column rank of it. Oops, can't write today. So on the one hand, the dimension of T is the column rank. On the other hand, I want to bring in the row rank from the null space. How? And remember, I'm starting with a matrix, and I'm going to worry about some rows. That should maybe give you a hint about what I'm going to do. I'm going to look at row. So the point is, yeah, maybe I should have proved that initially. If I take it's part of the homework, right? So if I take any matrix and I perform some row operations on it, then it is row equivalent, right? The spans stay the same. That's one of the homework problems, homework 3 or 4. The span of the rows doesn't change, and therefore any matrix, if two matrices are row equivalent, they have the same row space. They have the same spans of the rows. In particular, the row reduced echelon form, and it shows up again to save the day here. The row reduced echelon form of a matrix has the same row space as the original matrix itself. This is the rank. But as far as the nullity part goes, we'll see this. But yeah. Okay, so first of all, okay, we will use this later. So let me say this: that by homework 3, since A and RREFA are row equivalent, and let's not do this, are row equivalent, they have the same, the spans of their rows agree. The spans of their rows are equal by homework 3, by homework, I think 3, i.e. Okay, which means again, of course, taking dimensions. So that means the row spaces are the same. Taking dimensions, the row rank of A equals the row rank of RREF of A. But now let's look at this row rank of RREF of A. How do you write down the row reduced echelon form? You write down, so how does it look like? It has some leading 1, then some bunch of things. Then another row, the first entry of which must also be a leading 1 and no other entries above and below it. also some other non-zero entries, and so on, right? And all the zero rows are below. So every non-zero row is above and it has a leading one. So the row rank, and also since those leading ones occur in different places, of course they are linearly independent because you can check, right? If any linear combination is zero, then look at the positions of those leading ones. There are no other contributing coefficients in any of the other rows in that column. So every coefficient, every leading one times that coefficient must be zero. So the coefficients are zero. Row rank of this thing. Okay, and the point is, so let me say that in a separate point. The non-zero rows of RREF of A are linearly independent. Because just look at the so Ci, let's call this Ri. Ri equals 0, or let's call him Ri transpose because column transpose is row. But then look at the leading ones columns. The coordinates corresponding to leading ones. The coordinates corresponding to leading ones are precisely Ci. And they must all be zeros because there is nothing, no other column has any non-zero entry there. Yeah? So those must be zero. So now because of this, the non-zero rows are linearly independent, every other row is zero. So these are therefore a basis of row space. But what does that mean? It means that the row rank here is exactly the number of non-zero rows. So from these 2 points we conclude that the row rank of A is the row rank of RREF, which is the dimension of the row space. When the dimension of the row space is given by the size of the basis, which is the number of non-zero rows. Is the number of non-zero rows in the row reduced echelon form. But now we know something about the number of non-zero rows. This is the number of free variables. Or pivot variables. Sorry, this is the number of pivot variables, not free. The whole point is there pivot variables, and that is n minus the number of free variables. So every other variable is free, and these are uniquely determined because the coefficient was 1 from the pivot variables. Okay, great. This is where we stop. Okay, so on the one hand, I have that the rank of T is the column rank. On the other hand, I have this, that the row rank of A is n minus this. Okay, so I have these two equations. Let's call this equation 2. Let's call this equation 1. And now I need to use 2 more facts. And then we are done. There was a class previously, a few classes before, I told you of an example of a basis. And I said that that basis would come in important. So, in the previous class, we wrote a basis for the kernel. So far I have not brought in the kernel, right? So that's the point. Okay, so far I have just talked about the row rank and the column rank equals the column rank of A is the rank of this transformation. The row rank of A equals n minus the number of free variables in here. So far, I have not brought in the nullity or the kernel of T. Right? So now we are going to bring that in. So now let's see this. Yes, great. So now so So here's what I'm trying to say basically. I'm trying to say that the column rank of A is what it is. On the one hand, it is the rank of T. Okay. Now let me also, okay, there are a few steps. I have to get to the row rank of A. Okay, the row rank of A. You have to get to row rank of A. Fine. Okay. This is going to be the end of my proof here. So if I can, I'll fit it in here. Okay. So on the one hand, it's the rank of T. On the other hand, from the row rank, we know that that is equal to n minus the number of free variables. In the row reduced echelon form. Okay, great. So far so good. Okay. Now the rank of P is, this is where I use the rank nullity theorem. That is my next step here. This is n minus the nullity of it. Then n minus the nullity of T. But what is the null space of T? That is the final step. Now, the null space of T, the kernel, the nullity of T is the dimension of the null space. Well, what is the null space itself? This is precisely the set of all vectors that T takes to 0. But what is T of V? It is precisely AB. So it's V such that AB equals 0. Sorry, there's no W, it's just F to the N. And in the previous class, this is where we write down that missing connection. Yeah, we wrote down the basis for this with one vector for each free variable. With one vector for each free variable. Therefore, now we can write this down. So it's n minus the nullity of T. But now, because the nullity of T, the basis of the null space is in bijection with the number of free variables, this is equal to n minus the 3. So nullity is equal to number of free variables. So n minus that equals n minus this, and that is exactly the row rank. And hence the row rank equals the column rank. Okay, so that's exactly the point. That's why the rank nullity theorem is the missing bridge. We could come from here to here. That is easy. We could come from here to here. We did in a previous class. This is the previous class. And we could go from here to here. The missing question is, why is the nullity of T? Sorry, we could go from here to here, we could come and do all the way here. Why is this bridge there? And the reason that bridge exists is called the rank nullity theorem. Okay, so I guess that's it for today. We will continue on next week. Let me just step aside if you want to pause and take a picture, or pause and take notes. Okay.